Okay, and I guess let's get started. Do you have any question from this time? If not, then let's start with the next session. So today we are talking about 3.5, changing of basis and coordinates. I think this section is relatively easy. There is only one or two concepts here. Okay, so first let's talk about what's coordinates. So coordinates in R2 is basically the numbers when these are two numbers when you write down your vectors in R2. Okay, so we know that every vector in R2 is described by those two scalars x1 and x2, and we write them as column vector. And yeah, so these two numbers, they can be single of coefficients multiplying those two standard basis elements. So we know R2 has the standard basis E1 and E2 being this 1, 0 vector and the 0, 1 vector. And so any vector x1, x2 can be written as x1 times this 1, 0 vector plus x2 times this 0, 1 vector. So it's x1 plus x1 scalar times E1 vector plus x2 scalar times E2 vector. Okay, so yeah, this should be relatively simple, and I think you learned this in probably middle school, that we have a geometric interpretation here. So we have any vector x in R2, and so it can be written as the sum of two components, one component in this x direction and another component in this y direction. Now this x direction is E1 and y direction is E2. Okay? And so these x1, x2 are what we say what we call the coordinates. Okay? So this is the origin of this coordinate concept. Okay? And we'll keep talking about this coordinate concept in this section. Okay? So it's the coordinate of this x1 and x2 number is the coordinate of this x vector. And but coordinate depend on two things, depend on your vector, and they also depend on the basis. So it's the coordinate of x with respect to standard basis. So it's when we choose our basis elements being this E1 vector and the E2 vector, then the coordinates, there are two scalars, is this x1 and x2 number. Okay. And yeah, and then we can think about coordinates in different bases. As we said, as we know from previous study, any vector space and have many bases. So we still stay in R2, and we can choose different bases for R2. So say there are some y and z bases, then we can write our x in different linear combination of y and z. And so in terms of picture, it's sometimes like this. So maybe your y look like this and the z look like this. Then your x will be say 3y plus z. Okay, so you can have different linear combination of y and z, and then it becomes x. Okay, and now we need to go back to use something that we talked before. So we say way back in 3.3, we say that by theorem 3.3, whenever you have a basis, then you can have this alpha and beta being unique. So whenever you have basis, then this alpha and beta number is unique. So these coordinate numbers are well defined. Okay? And back in 3.3, we don't actually have the idea of a coordinate. Sorry, don't have the idea of basis. And so this theorem is talking about linearly independent. Okay? So whenever your vectors are linearly independent, then anything inside your span can be written as a unique linear combination. Okay, so here we use the both properties of the basis. So we use that. So any vector inside the vector space is inside the span of your two vector because it's a basis, and also because it's a basis, so everything is in that span. So it can be written as a linear combination between y and z. And also YZ are linearly independent, so you can write the x as a unique so the linear combination is unique. Yeah. So we use both property of the basis here. Okay. So we know that whenever we have a basis, so any vector can be written as a unique linear combination. of the basis vector. And so the linear combination has coefficients. So the list of those coefficients are called the coordinates. Okay? And so this list we put that into vector, actually a column vector, and it's called the coordinate vector of your coordinate vector of your original vector, this vector x, with respect to this order basis yz. Okay. So so here we have a bit of a different notation here. So we have this notation for order basis. We use the square bracket here instead of the usual curly bracket here, because curly bracket means a set, and set don't have ordering. So set of yz equal to set of zy. But the order basis yz is different from order basis zy, because when we write this, we mean that we are also recording the order. Okay, so maybe something here. So a set, we don't care about the ordering of a set. So y vector, z vector equal to the set of z vector, y vector. But if we are talking about ordered basis, so it's order list, then this thing doesn't equal to this thing. Okay. It's not too hard, just a notation thing. Okay. And so to talk about, we need this idea of order basis, only because the coefficients, these coefficients, these coordinate vectors, has a one-to-one correspondence to the basis basis elements. So you see this alpha is correspond to y and beta is correspond to z. So we need to record the ordering of yz. So this ordering of alpha and beta will match the ordering of y and z here. Okay. Should be relatively easy concept. And yeah, so let's see an example in more numbers. Let's say we have y and z equal to those two vectors, 2, 1 and 1, 4. And so first we check their basis. And we know R2 already have dimension 2, and so we only need to check that they are linearly independent. And then to check whether a basis is linearly independent, excuse me, there is an easy way to do this. That's you just calculate a determinant, because when you put those vectors into a matrix, they must form a square matrix. So you can just check the dependency by calculate the determinant, and the determinant is not zero, so we know they are linearly independent. So this is a basis. And as we say, we can have some x vector being this maybe 7, 7, and we see that they are it is a linear combination between y and z. And here is coefficient being 3 and 1, and so this 3 and 1 is the coordinate vector. So coordinate vector is this 3, 1 vector, and we have seen the geometry here. Yep. So that's the idea of coordinate vector. Well, okay. Okay. And yeah, now let's talk about changeable basis in R2. Okay. So for example, now we have two new basis vector u1 and u2, being this 3, 2 and 1, 1. And let's first do the changeable basis from standard basis to our u1 and u2. Okay, so we have our vector x being this x1, x2, and we want to find its coordinate in u1, u2. And then we have another problem. So we have already have the coordinate vector in u1, u2. So we have x equal to some c1 times u1 plus c2 times u2, and we want to find its coordinate in e1 and e2. Okay. So let's do these two problems. And so the first one, so you have some coordinate. I guess it's sorry. Let's do the second one first. Okay. So we have we see that u1 is the 3, 2 vector, which equal to 3e1 plus 2e2, and u2 equal to this 1, 1 vector equal to e1 plus e2, and so you can write yeah. And so if your vector x equal to c1u1 plus c2u2, and then you can write the u1 u2 in terms of e1 e2, and you multiply everything out, you get this 3c1 plus c2 u1 plus 3c. And so you multiply everything out and collect the terms with e1 and then e2, then you get those linear coefficient to e1 and the linear coefficient to e2. And so you see, so now we have solved the second quadrant. So we see x1 equal to this number here, and x2 equal to this number here. Okay, so we know that if we have c1 and c2 as a coefficient to u1 and u2, then the coefficient to u1 and e2 will be this like this equation. So x equal to x1, x2, and equal to 3c1 plus c2, and x1 equal to 3c1 plus c2, x2 equal to 2c1 plus c2. Okay. And they can be written as this matrix multiplication. So you see this 3, 2 is this u1 here, and 1, 1 is this u2 here. Okay. And I guess it's another way to see this is we can have a direct interpretation here, because this matrix equation, it can be written as c1 times 3, 2, which equal to u1 plus c2 times 1, 1. Because this is something we talked in chapter 1, we say that when we have a matrix times multiplying a vector, then we can view this as a linear combination between the column vectors of the matrix. Okay? So matrix as the column 1 being u1 and the column 2 being u2, and if multiplying c1 and c2, then it's equal to c1 times the first vector plus c2 times the second vector. Okay, and anyway, so we can write this. Now this is a very useful definition here. So when we have this u1, u2 order basis, we can define this square matrix. That's you put u1 and u2 as a column vector and write down a square matrix. So we can define this u as this square matrix, u1, u2 being, you put the first column as u1 and the second column as u2. And now we can write down this nice algebraic expression. So we have this x vector, which is coordinates in standard basis, just equal to this u matrix times u coordinates in u, so u times c. Okay, and so this u is called actually, yeah, this q is called a transition matrix from your basis u to the basis e, standard basis. Okay, so yeah, by infinite is a transition matrix from order basis u1, u2 to standard basis e1, e2. Okay. And yeah, so here we answer the second question. So how you go from the coordinate in u to coordinate in x is you multiply this u on your coordinate in u, so u times c become the coordinate in standard basis x. Okay. And with this equation, we also know how to write this thing, because this thing we also know how to solve 1, because 1 is just the reverse of 2. Okay. And so we, because the u is non-singular, we can just multiply u minus 1 on both sides, and then we have c equal to u minus 1x. And then we can think about why u is non-singular. Anyone want to answer why u is non-singular? Okay. And anyway, okay, so u is non-singular, very similar to the previous case here. Non-singular because we have that those two things. When u1, u2 bases, they are linearly independent, so the determinant will be non-zero, so the matrix is non-singular. Okay. And it's non-singular, so we can have c just equal to u minus 1x. And yeah, then u minus 1 is another transition matrix, is a transition matrix from e1, e2 to u1, u2. Okay. And yeah, so let's write this as the picture is like this. So we have a U1, U2, and you go to E1, E2, and you have this matrix U here. Okay. And let's keep about this. Let's talk about this first. So we have C equal to C1, C2, and those are coordinates for U, and X equal to X1, X2 is a coordinate for the standard basis, and we have X equal to UC, and so U is a transition matrix from C to U, C to standard basis. Okay. And also we have a U-1 being the transition matrix from E1, E2 to U1, U2. Okay. And is a U and the coordinates, remember that they need to satisfy this equation. So C1 times U1 plus C2 times U2 should equal to X1 times E1 plus X2 times E2. Okay, and I guess easier way to so in terms of how should I say? In terms of those Rn, in terms of Rn, I think it's there is an easier way to memorize this thing. It is so it is also for later part of the course. So we have this X equal to UC, but there is a more symmetric way to think about this U matrix. But because for me it's a little harder to remember whether this U is from U to E or from E to U. But the easier way to remember this is you can think about you also multiply X with other thing. Okay? So really this equation, as we talked about, is for this equation when you write down in matrix form. This means that so this side of the equation means U times C. This is the coordinates. The coordinates times the vectors and summing together. So we use the coordinates to make a linear combination of those vectors. So this is written in matrix form. This will be U times C. So this U matrix be writing down basically putting the order bases together into a matrix. It is U matrix, and multiplying the coordinates with respect to U, you get a UC on one side of the equation. And the other side of the equation is actually just equal to this E1, E2 times the X1, X2. So we can also write the E1, E2 vector times the X coordinates. And now the standard basis E1, E2 is when you write out it into the matrix, it's just this identity matrix being 1, 0, 0, 1. Okay? Because it's a standard basis, so E1 is this 1, 0, and E2 is this 0, 1. Okay? And so this equation here basically actually just says that you are just translating this equation. Okay? So we have a C1 U1 plus C2 U2 equal to X1 E1 plus X2 E2, and you write down those in matrix form. Then this C and U become U times C, and this X and E become identity matrix times X. And we know identity matrix X, just identity matrix times X equal to X, and so what we get is X will equal to UC. And I like this interpretation a little more because it's symmetric with respect to U and E. So you have identity. This identity matrix being this matrix for standard basis, and this U matrix being the matrix for U vector. Okay. So Ix equal to UC, and that means X equal to UC. So U is will be a transition matrix from U to X, and so this will be a nice way to remember things in Rn. Okay. So this is nice for Rn, and I guess we mostly do changeable basis in Rn, but I guess this is less general because if you have abstract space, then you don't really have the standard basis to write things. But it's nice for Rn. Okay, and so let's see more example. We have u1, u2, and x, and let's try to write x with respect to u1, u2. And yeah, so basically we do this thing. So we have x equal to uc, and then we know c equal to u minus 1x. And so we can write down u being this u1, u2 vector, u1, u2 together being this matrix 3, 2, 1, 1, and then we can calculate the u minus 1. And we skip the part where you calculate the u minus 1. U minus 1 is this 1 minus 2 and minus 1 3. Hopefully we do the calculation correctly. And so we just have c equal to u minus 1x. And it's you have a u minus 1 multiplying on this x vector. And this is just matrix multiplication. Become this 3 minus 2 c1 c2 vector. Okay. And yeah, we can check our answer is correct. So we have this 3 and minus 2 multiplying on our u1 and u2, and u1 and u2 being this 3, 2, 1, 1, and you do calculation, you check all this actually correct. Okay. So we get back this x vector. Okay, and we have more examples. So we have b1 and b2, and we want to find the transition matrix from E1, E2 to B1, B2. And we know the transition matrix is just write down B1 and B2. So because x equal to b times the coefficient of b. And so transition matrix is write down this, so 1 minus 1 and minus 2, 3. Okay. And then we want to determine the coordinate when we have some x with some x equal to 1, 2, and we want to find the coordinate in this b1, b2. So once again, we want to calculate b minus 1, and then we have c equal to b minus 1 times x, and equal to this number. Okay, any question? Okay. So then now let's go to more even more generalization. So let's think about changing from two bases. Neither of them are standard bases. Okay, so we want to see a change of basis from v1, v2 to u1, u2. Okay, and yeah. So once again, we want the S matrix. So now we want the S matrix that change from v1, v2 to u1, u2. And once again, it's easier to write down this equation. We know we want this c1, c2. Now, we want want the vector that has coordinate c1, c2 in terms of those v, and also then we'll have a coordinate d1, d2 in terms of those u. And this means that this linear combination of v with c1, c2 will equal to this linear combination of u with d1, d2. And that means, I guess I should really do this in one page. Okay. So that means, sorry. So let's write it here. So yes, we actually have important thing to remember is we have these two equations. Okay. So if we write down those two things, once again we think about this as a matrix multiplication. This means that we can write the v1, v2 into this v matrix, and u1, u2 into this u matrix. Then we have v times c vector equal to u times d vector. Okay, and from here, then we can get a relationship from c and d. Okay. And so here, once again, because the v1, v2 is the basis, u1, u2 is the basis, so both the v and the u will be invertible. It will be non-singular. So we can have, so we can just have move this v to other side by -1. So we just have the c vector equal to b minus 1 times the u vector times the d vector. And yeah, so we have find out this s vector. So we want to go from oh sorry, here the s, I think I have so this line I forgot to change. Okay. So s is the other way around, right? So we want d equal to S times C. Okay, sorry. And yeah, so and another thing is C equal to S minus 1 times D. Okay, and okay, so we want the S vector to be other way around if we want this. So and let's also write this better. So this U. Okay, and yeah, so we want D equal to something times C. So we move this U to other side, and we will have a D vector equal to U minus 1 V times the C vector. Okay. And yeah, but I think the really important thing is you should remember the middle part. This is easier to memorize. If you just try to memorize S, I think it's a little harder to know whether S is going from B to U or U to B. But if you try to remember this equation here, you just have the V matrix times the V coordinate equal to the U matrix times the U coordinate. Okay, and yeah, then you want coordinate to other thing, you can just move this UV around. Okay, and yeah, the next slide basically says this thing. We can say this V matrix for V and U matrix for U, and we'll have this equation. So this V matrix times V coordinates will equal to the vector you have, and will also equal to the U matrix times the U coordinate. And you can move things around to go from C to D or D to C. So D, if you want from C to D, and will be U minus 1 times V. Okay, and yeah, and yeah, so we see that we're going to want to go from, go from U. So if we want to go from the V coordinate to U coordinate, then we need to multiply with this U minus 1V. So this is the transition matrix. Okay. And yeah, so then that's almost finished what we want to talk about. So, but let's see some examples. So we have a coordinate. We have some U vector and V vector, and so the guess it's a little UV. Yeah, I guess we didn't say the U vector and V vector here, but okay, it's a little weird. We write down the V and the U in a solution, okay, and oh, sorry. So I guess here we should change those two things. Okay, sorry. So this should be quotient and this should be answer. Sorry if I didn't check this. And yeah, so the quadrant is here. So V are those two vector and U are those two vector. And anyway, we want to change it from V to U. And so we have this U minus 1V. And so we skip all the middle calculation. So we have the well, V matrix is here, so V matrix here, and we can have a U matrix, and they will calculate U minus 1. I think we actually calculated this in the question before, and U minus 1 will be this matrix. So you calculate U minus 1 and you multiply the V matrix, you got this matrix. Okay. And yeah. So anyway, that's the idea, and you can think about this in other way around. So you can think about so this is a bit a bit more general. So you think about there is a standard matrix. Then if when you have a changeable matrix, you can think about V as a transition matrix from V to standard basis, and U is a transition matrix from U to standard. Then you change from standard to U is a U minus 1. So you want to go from V to U. It's you do V first, then U minus 1. So it's U minus 1 and V. Okay. So it's another way to memorize the transition matrix being U minus 1V. But also you can just remember VC equal to UD. Okay, and yeah, we talk about things in R2, but obviously all the things we are doing can be extended to Rn. Okay, so let's see an example in R3. So we have first way for the three basis vector v1, v2, v3, and another three basis vector u1, u2, u3. Okay. And we want to find the transition matrix from this basis E to basis F. And yeah, we have VC equal to we have so let's say this coordinate equal to C. Say we have a coordinate equal to C here and the coordinate equal to D here. Then once again we have a VC equal to UD, and so then we have D equal to U minus 1. Let's write minus 1 better. U minus 1 VC. Okay, and yeah, so the transition matrix should be U minus 1 times VC, and okay, U minus 1 times V, and and also then you have coordinate X and Y. So X and Y in turn that has a coordinate in V, and then we want to find the coordinate in D, so coordinate in F. Okay. So here we have a X equal to linear combination of V, so we have a coordinate being this 3, 2, and minus 1 here, 3, 2, and minus 1, and Y we have 1, minus 3, and 2 here. And so we can just multiply with the transition matrix to get it to coordinate in F. And yeah, so the only thing we need to do here is basically calculate this U minus 1V here. And so yeah, so we have U here and V here, and we calculate U minus 1 becomes this matrix, and times V, and it becomes this matrix. And so X in terms of F is you just multiply this transition matrix here with the coordinate in E, and the coordinate in E we see is 3, 2, minus 1. Okay, so just a more matrix algebra, you get this coordinate in F, and similarly for Y you have a coordinate in E, those 1, minus 3, 2, and you get the coordinate here, and you can verify this by doing the calculation here. And yeah, so I guess we didn't really say, but we do this example in R2, R3, and obviously you can extend this to Rn. And yeah, I think we can stop very early today. So there is not too much for this section. So yeah, so here we talk about order basis and the coordinate. So we have some order basis. Order basis we have this weird notation, curly bracket, U1 and U2, etc. And then we have a coordinates. These C1, C2, C3, etc. Being that whenever you have some vector x, then you can write it as a linear combination of your order basis, and then these coefficients for your linear combination. So those scalar C1, C2, etc. Is your coordinate. And then we can have this transition matrix U is so transition matrix from your order basis to the center basis. You just write your basis vectors as columns and put them together into a matrix. So this is transition matrix U is very nice. And we have that coordinate. We have that whenever we have different coordinates with for different bases, then the coordinates times the transition matrix for the basis will equal to the other coordinate times another transition matrix. This VC will equal to your HRD vector times UD. Okay. And then from this equation, you can calculate how you change from one coordinate to another coordinate. Say D here will just equal to U minus 1 times V times U or C. And the transition matrix from your let's see, do I got this mix up? So D is I think it's a transition matrix from B to U. Sorry, it's still a bit easy to confuse. So this should be from B to U. Okay. And yeah, so you have C being coordinate for V and D being coordinate for U. And then this U minus 1 V will be transition from this V coordinate to U coordinate. Okay. And I guess because okay, I will fix the notation later because it's a bit confusing. So yeah, so because I have a C with U here and B with C with V here. Okay, so on the second part we have C1 V1 plus C2 V2 plus equal to D1 U1 plus D2 U2, etc. Yeah, I will try to fix the notation here and upload the slide. Okay. Any more question? If not, I think we can stop really today, and we'll continue on next Monday, and we'll try to. I think we can try to finish 3.6 in next Monday, and next week we'll have our midterm. Yeah. So yeah, see you next Monday.